Alright, welcome to another AQA AS chemistry video. This video is on equilibrium constant. However, I didn't really miss out, but I didn't really cover this part of increasing rates, and I'm not bothered to go back and edit that delete the video and edit it again and then put it back in. But this was part of the increasing rates, and it's something that you kind of already know, but it was just, I talked about the effect of catalysts, the effect of increasing the temperature on the rate of reaction, and how that affects the Maxwell-Boltzmann distribution curve. But this part here is just about I don't think I talked about pressure, but I definitely talked about temperature and the effect of the catalyst on the effect of the Maxwell-Boltzmann distribution. And I said that the only thing that can increase the area underneath the graph represents the number of molecules in a sample, right? And I said that doesn't change when you change the temperature, because obviously the law of conservation of mass suggests that, well, it doesn't suggest, it tells us that no atoms can be created or destroyed. So when you increase the temperature, the graph would change. It may shift to left or right. I haven't got the example with me here. It may shift left or right, but overall, the area underneath the graph would be the same. The only thing that can increase or change the area underneath the graph is if we increase the concentration, increase the number of particles that we have in our sample. So the effect of concentration on reaction time, right? If you increase the concentration of reactions in solution, the particles will on average be closer together. And if they're closer, collisions are more frequent. And if collisions are more frequent, there'll be chances for particles to react. So the closer they are, there's going to be a higher frequency of collisions because they're more closer to one another, and it's a high. If I have a jar, right, and I put, like, I don't know, like some beads in them, like if I put 2 beads in them, there's a lower likelihood of those beads colliding with one another compared to beads that, if I put like 6 beads in that same jar, I'm increasing concentration, right? And there's going to be a higher likelihood that those beads would collide with one another. Now, generally in chemistry, when we're talking about collisions, you're talking about collisions between the walls of the container, but there are sometimes collisions between there obviously are collisions between the particles themselves. So if you increase the concentration, you're increasing the numbers of collisions. So if reaction involves gases, increasing the pressure of the gases works just the same way, because you're raising the pressure pushes all the gases particles close together, increasing the number in a given volume, and this increases the frequency of collisions. So which would increase the reaction rate. So the more if you increase the pressure, right, you're basically kind of making the volume those gases are at smaller, because and in that sense it will make them more close together, and therefore there'll be more collisions between those particles, and enough of those particles will have the more collisions are, there's a higher percentage chance or higher likelihood that those particles will successfully collide and react. So you would increase your rate of reaction. This is what your graph would look like, right? So it's not what it's not what you'd compare. If you compare this to other graphs, so the red line is when that's a low concentration, right? I was gonna ask you which one's the high concentration, which one's the low concentration, but I think it's pretty obvious, right? This is a low concentration, and this is a high concentration. Oh, actually, it's pretty easy. What I want you to do is I want you to try and describe the two graphs. If I had to give you a question that said, describe the differences between the two graphs, right? Or describe and explain if you want to. Actually, no, first of all, just describe the two differences between the graphs. How would you describe it? I'll take some time now to try and think of a way to describe it. So how I would approach it is that I look at, when you're describing a graph, you always compare the x values and the y values. So if I was talking about this graph, I'll say that the second graph, or this, let's just say this green curve, right, which is the high concentration, has a higher number of particles, a high x value, and overall more of those particles have higher energy, right? So there's a high number of particles that have high energy compared to the low concentration graph, where there's less particles and less of those particles have higher energy. And if we're comparing the activation energy, is a much higher concentration of, because the concentration is the particles, right? There's a much higher concentration of particles that have activation greater than the activation energy, greater than or equal to the activation energy, compared to the low concentration. Now, if I told you to explain this, you'd start to say the reasons for it, right? This remember, you have to make sure that you don't confuse describe and explain. If you get an explain question, if you get a describe question and you start explaining, you get no marks. Like it's the same vice versa. If you get an explain question and you start describing the graph, you'll get no marks. If I was to explain this graph, I'll say the reason why. So say when there's a high concentration, there's more particles in the same volume, and therefore there'll be a higher percentage or higher likelihood that there'll be more successful collisions per second between the particles, and therefore therefore there'll be more successful collisions per second, and therefore there'll be more particles with the activation energy to successfully collide and react, and that would increase the rate of the reaction. And that's what's pretty much happening here. So this is the activation energy, and that's the activation energy line here, and this pink kind of like, I've compared these two. So this is the number of particles. Remember, the area underneath the graph is the number of particles, and this blue area here is the number of particles that have the activation energy to successfully collide and react when there's a low concentration, compared to this pink area here, which is the area underneath the graph. The pink and the blue, it should be the pink and the blue area really. This pink region here represents the number of particles extra on top of the blue particles that can successfully collide and react. So everything underneath here, from here to here, that's all the number of particles that can successfully collide and react when it's a high concentration. The pink one here is to show that how much extra on top of the low concentration, right? But ideally, all of that is how much is the number of particles that have the activation energy greater than or equal to the activation energy to successfully collide and react. All right, now that I'm done with that, I'll finally move on and go back to the actual video, which is equilibrium constant. This is now, I think this is the last topic on equilibrium, I believe, or maybe second to last topic on it. The equilibrium constant is a constant for a particular reaction at a particular temperature, right? And this kind of K here, it represents constant. Even in maths, you see the K whenever you're doing, for example, direct proportion, right? It says, if they say A is directly proportional to B, you can also write that as A is equal to KB. This K just represents a constant. It represents a value that's always the same, or something, or along those lines, right? And you can work out that constant, and each reaction has a particular constant. So the equilibrium constant is a constant for a particular reaction at a particular temperature. An equilibrium constant greater than 1 indicates that the forward reaction is dominant. So if the value for K is or the value for Kc, I should say, is greater than 1, you know the forward reaction is favored. If an equilibrium constant is less than 1, this indicates that the backwards reaction dominates, right? Yeah, so there's different constants. Kc represents the equilibrium constant for concentration. That's what the C represents. We can get Kp, which is in year 2. I'll go over that when we get to year 2. That's pressure. Kw, which is the equilibrium constant for water. Ka, which is the acid dissociation constant. These are all things, those are the ones that you need to know for A-level chemistry. But in general, in chemistry, there's loads of different types of constants that you'll end up finding. But the ones that you'll need to know for chemistry, which I haven't, this is the first one I've gone through, but it's Kc, Kp, Kw, and Ka. The rest of these are YouTube, but first we just need to know what's going on, right? So the maths. This topic includes maths and it requires equations. The equations are very simple, but don't get thrown off by all this. It's actually very simple. So for a reaction, let's say this reaction happened as A moles of A plus B moles of B goes to form C moles of C plus D moles of D. To write the equation for equilibrium constant, it's always, the Kc is always equal to, get my pen, Kc is always equal to products over your reactants. So, and now I'm going to go a bit more just saying that products over reactants. It's your moles of products over your, well, I'll go through it, right? So this bracket here represents your concentration. So this is your concentration. So it'll give you, say, said moles of, say they give you said moles of C, right? They give you said moles of C, and you have to work out the concentration of C. So once you work out the concentration of C, this bracket here represents the concentration. This little c here represents the mole. So this C here, this capital C here, is represents the concentration. This lowercase c here represents the which it represents the moles, and the moles is always the exponent of your reaction. So the moles is always the exponent of your concentration. So if I have, let's say I had 0.5 moles per dm cubed of C, right? And I had, let's say our value for this 3 moles of C. Let's say that there was, yeah, let's call this lowercase c, or the moles of 3, there's 3C, right? Therefore, this would be 0.5 to the power of 3. Oh, don't know why that happened. Yeah, don't know what happened there. Anyway, 0.5 to the power of 3, and that's what it is. So I'll give you an example here, and I might go through another question, right? I'll probably go through a question after this at the end. But so let's say this is this reaction here, right? So propanol plus 5O2 goes to form 3CO2 plus 4H2O. Try and write the equation. By the way, in the exam, you do get marked for just writing out the equation, right? So try and write out this equation. I'm not asking you to do any calculations. I'll go through that towards the end of the video, but try and just write the equation for this reaction. Pause the video now and try and do that now. All right, so I'm going to assume that you've done that. So what this is for me, how I do this, is that the CO2 cubed, because it's always reactants over products, right? And when we look at our reactants, so there's 3 moles of CO2, so it's CO2 cubed, and it's multiplied by H2O to the power of 4, because we have 4 moles of H2O, over our reactants, which is propanol, right? And we have 1 mole of propanol, so I could write propanol to the power of 1, but in maths, remember, we don't write to the power of 1, because anything to the power of 1 is just as it is. So it'll just be propanol, so CH3, CH2, CH2OH. You could just write C3H7OH if you wanted to, and there's 5 moles of O2, so it'll be O2 to the power of 5. So hopefully this makes sense to you. It's very simple. I may have not have described it in the best way, but this is very simple. And of course, there'll be some times in a question where if the number of moles is balanced on either side of the equation. In this case, it's not, right? There's 7 moles on this side and 6 moles on this side. But say that it had a reaction, right? And there's an equal number of moles on either side of the equation. So it's 2 moles here, so 1 and 2, 1 and 2, right? You wouldn't need to work out your concentration, because if the moles is equal on either side of the equation, you can just do, you don't even have to use the concentration in your reaction. You can just use the moles of the reaction straight from your from the data where they gave it to you. Alright, so the square brackets in this case indicate concentration. When you do year 2 and you do KP, don't do square brackets. Square brackets is specifically to show concentration only. The indices are the stoichiometrics of the components, which just means that they're indices of the components, and these numbers for each species in the reaction equation are represented above by the lowercase letters. So calculation, so we may be given the value of Kc, so we will have to sub the values in for each concentration. This would give us a value for Kc, and make sure to sub the units of each concentration into the calculation to make sure the Kc value has the correct units. So we can also be given the Kc value, and maybe asked to rearrange the equation to find a concentration. So this part here, that can happen. So they'll give you the value for Kc, and they'll want you to work out the concentration of CO2. All you're doing is just rearranging your equation. And if you know basic maths, it's a simple thing to do. The one thing I didn't mention here, which I should have done before, right? Before that, I'll show this example here, but it's also this part here. You also need to work out your units, right? Because if I'm multiplying so and so to the power of this and that, I have to also be aware that the value of the units may change. So in this case, you have to think about it, it's for me, I can just see the 7 moles, there's the power of 7 on the top and power to 6 on the denominator, 3 and 4, 7, 1 and 5, 6. So I already know it's moles per dm cubed, but just to show you what I mean, you're doing moles per dm cubed, right? To power 3 multiplied by moles per dm cubed to power of 4 over moles per dm cubed times by moles per dm cubed to power of 5. Otherwise known as, you can just write this down as moles per dm cubed to power of 7 over moles per dm cubed over 6, and that's just equal to moles per dm cubed. In this case, in this scenario, the Kc is just equal to moles per dm cubed, but if you had, let's say this was a 7 and this was a 5, right? Let's just say for this example that it was a 5, because your Kc value, the units for your Kc value, or any equilibrium constant in general, apart from constants, certain ones that are always the same, but it's not always the same value. It can even be, it's always changing, and there is a situation where you can get no value. So I'll give you an example of this, right? What will be the moles per dm cubed for this example here? It would be moles per dm cubed, well, moles per dm cubed squared, right? Because 7 minus 5, but squared, right? Now you'd have to write this in your units, and you get a mark. They'll give you a space to write your units, and you get a mark for writing the correct unit as well. Moles to the minus 2 will be moles squared dm to power of minus 6. That would be the units if that was the answer here. Let's try another example, right? So what would be this? Ooh. If you found out that this was your value, right? How would you write this out? Alright, so it'll be this, right? I gave you a bit of time to write that out. So it will be this. It's moles per dm cubed to the power of minus 2, also known as moles to the power of minus 2 decimeters cubed to the power of 6. You just flip it. This would become a minus 2, and that's to the power of 6. You remember when you multiply indices, you're multiplying, you just multiply the indices. When it's a bracket, you just multiply the indices. In this case, 1 to the power times by minus 2, minus 3 times by minus 2, 6. And it's very easy to see this. I mean, when you do a lot of these questions, it becomes very, very easy to come and see this. And then last one of all, I've seen some people get caught out by this example here. But how would you write this out? Here's a lot. This is the last example. How would you write this out? All right. So a lot of people have been unfortunate. It's some people might get caught out by this. I don't, but some people may get caught out by this. Some people might just go and say they just cancel each other out, right? So it's just this. No. 7 minus 7. Think of it as 7 minus 7, and that's 0. It wouldn't, if it was 7 and 6, that would just cancel out to give you multiple dm cubed and the power of 1. That would be that, but it's not. It's 7 minus 7. Think about like 7 minus 7, and it'll be anything it'll be to the power of 0. Anything to the power of 0 is 1. But in your exam, if you get this situation, the correct thing to write down is no units. And if you know, if anything, remember this is a unit, right? If your unit can't be 1, your unit is, you know, multiple dm cubed, and if there's no unit, you can just write no units. That's a mark in the exam. That's what they want you to say. All right.